What's up, guys? So some people wanted to see the derivation of the rotational inertia using an integral definition. So this isn't something that's necessary for you to do. You won't have to do this on an exam or anything like that. But it can be sort of interesting to see how to work with this equation. So what I'm going to do here is I'm going to derive the moment of inertia for a solid sphere using the moment of inertia for a what is that? Thin disk, like a nice thin disk that has mass all the way throughout it. So there are ways to do this one strictly using like what is it? What would it be? Spherical integration. So that's one way to do this one. Now what I'm going to do here is I'm going to do it using just rectangular coordinates because that is what everyone is familiar with, and that's prereq for this class. So let's start out. The first thing I'll do here is I'm going to go ahead and draw a little bit of a picture of a sphere here. So you always gotta, it's a nice round thing. Whoops, it's an ugly sphere. Let me take that again from the top. So what I'm gonna do is draw a picture of a sphere here. So we have a circle. There's the equator for the sphere. Something like this. All right, so that is an egg. It's not a sphere. Imagine it's round. And the equation we're gonna be using here is the integral definition. So I is equal to the integral of r squared dm. Now we're not actually going to be using this one. We're going to use, like I said, the rotational inertia for a disk. So essentially what this is you can break a sphere up into little disks, right? You have like a disk here, and you have another one here. So if we could add up all the rotational inertias for all of these disks, assuming that this is our axis that we're rotating around, if we can add up the rotational inertia for all these disks, we'll add up all these disks, and thus we'll have the rotational inertia for a sphere. All right, so the rotational inertia for a disk is, of course, 1/2 r squared times m. So di is equal to 1/2 r squared dm. So if we integrate, that means we're going to take the integral to find the inertia. We'll do the integral from negative r up to positive r in the z direction of 1/2 r squared dm. All right, so we need to do two substitutions. First thing we need to do is we need to come up with something other than mass to integrate over. So we want to integrate over a distance, obviously. Hold on, those don't come in yet until we, essentially what we're going to do here, though, is we want to integrate in the z direction. So if this is the z-axis here, then we want an integral in terms of dz. So we're going to sum up everything in the z direction. You can see I stacked my plates on top of each other in the z direction. All right, so what I'm going to do then is go to the density equation, and I know that density, we haven't exactly studied this yet, but density is equal to mass over volume. So that means that's equal to dm over dv. The volume of a sphere is 4/3 pi r cubed. So that means, let's see, actually I'll just go ahead and say that dm then is equal to rho dv. And since the volume of a sphere is 4/3 pi r cubed, that means that the derivative of the volume will be 4 pi r squared. So dm is equal to 4 pi r squared times rho. All right, so going back over here, we have that the inertia is equal to the integral of 1/2 r squared times 4 pi r squared times rho. And this would be dr here. All right. And actually, in this case, we're, of course, deriving in terms of z. So that's going to be dz, integrating in terms of z. All right. And that's not exactly correct. How the fuck did I get that? 4/3 pi r squared. Rho dv, dv is pi times r squared dz. Oh, I guess we're just going to take the area. Derivative of volume is the area of the fucking cross-section. Why am I such a dickhead? That's a good question. That's one that will also be on your exam, so let's go ahead and cover that. So, why am I such a dickhead? Well, the answer to that, it's multifaceted. The first reason that I'm such a dickhead is because I don't actually know what I'm talking about. So if that is an answer on your test, if that is one of the answer choices, of course, you go ahead and bubble that one in. I don't actually know what I'm talking about. But then the second part of this is, in addition to not knowing what I'm talking about, I refuse to admit it. So you can see that not only am I stupid, but I'm also ignorant about it. So it's sort of a two-part answer. Now on your exam, you'll only be given one of those as an answer choice. So you would choose either that I don't actually know what I'm talking about, or that I refuse to admit that I don't know what I'm talking about. And either of those would be a sufficient reason for why I'm such a dickhead.